This screen demo introduces an educational function of Visual FEA for instruction of finite element equation processing. The function covers interactive simulation of assembling stiffness matrices and force vectors into the system equations, comparison of different assembly methods, and node and element numbering for the computational efficiency. This demo is a continuation of the demo about element stiffness matrix of plane strain model in the file named planelm.mp4. So, the same plane strain model of the previous demo is used in this demo. In order to start the function, select System Equations item from FEM Simulation submenu of Solve menu. System Equations window appears on the right top, and Plane Element Selection button is automatically pressed. The window is composed of two parts. One is the control part with a number of tool buttons and drop-down lists, and the other is the display part, where the stiffness matrix is displayed. System equation window may be stretched or shrinked if necessary. The image of stiffness matrix is automatically adjusted to the changed window size. Numbering of nodes and elements has significant consequence in the assembly of the stiffness matrix. So, let's check the node and element numbers before examining this function. Choose Show Number item from View menu. Then, element numbers are displayed in red color on the image of the plane strain model. Press the Node Selection button, and choose Show Number item again. Then, node numbers are displayed in blue color. Going back to the educational function, let's examine the stiffness matrix window. The stiffness matrix and force vector are represented by small squares, each of which represents an entry of the stiffness equations. If you bring the cursor onto the image of stiffness matrix, the square under the cursor is highlighted in blue color. A yellow tick box shows the information about the entry represented by the square. The figures in the parenthesis are the row and column numbers of the matrix entry. The numerical value in the second line is the stiffness coefficient of the entry. At the same time, the degrees of freedom associated with the entry are indicated over the image of the model. A line arrow represents the direction of the degree of freedom. In the case of off-diagonal entries, 2 degrees of freedom are represented by 2 arrows. This display implies that the stiffness value is determined by the force displacement relationship of the 2 degrees of freedom. In the case of a diagonal entry, only 1 arrow is drawn, because the diagonal stiffness is equivalent to the force and displacement factor of an identical degree of freedom. Let's examine the force vector. Placing the cursor on a square representing an entry of the force vector highlights the square in blue color, and a yellow tick box shows the information about the entry. That is, the index number, I, and the numerical value of the force vector, Fi. At the same time, an arrow is drawn on the image of the model, indicating the corresponding component of the equivalent nodal force. The squares are drawn in 4 different types: filled black square, filled gray square, hollow black square, and hollow gray square. Entries with 0 value are represented by hollow squares. Gray color represents the entries associated with the degrees of freedom constrained by the boundary conditions. The stiffness equations should be partitioned before being solved. Partitioning is the process of separating free degrees of freedom from constrained ones in the stiffness matrix and force vector. Press Partition Matrix button in the window. Then, the partitioned stiffness matrix and force vector are displayed in the updated image. The assembled position of an element matrix can be identified by placing the cursor over the element in the image of the model. Move the cursor to the model image, and place it over an element in the model. Then, the element is highlighted in green color, and the entries of the matrix, assembled with the element matrix, are highlighted in blue color. Clicking the element freezes the highlight of the entries in red color. Place the cursor on the image of an applied force, Then the entries of the force vector, assembled with the element force vector, are highlighted in blue color. Clicking the force freezes the highlight of the entries in red color. Press Node Selection Tool button, and place the cursor over a node. Then, the node is marked by a small red square, and all the entries, related to the nodal degrees of freedom, are highlighted in blue color. The process of assembling element stiffness matrices can be graphically animated. Press Play Animation button. Then, element stiffness matrices are being assembled automatically by one element after another in order of element numbering. The speed of animation can be adjusted by selecting a desired item from the drop-down list, either slower or faster. The element under assembly process is represented by red color. Assembled elements are represented by gray fill. The assembly process can be examined stepwisely, using one step forward or one step backward button. One step forward button is used to assemble element stiffness matrices in the order of element number. Clicking the button will progress the assembly by one element at a time. Click one step backward button, then, an assembled element stiffness matrix is disassembled in reverse order of assembly. Thus, the assembly process can be examined while repeating back and forth. Another method of simulating the assembly process is the manual drag and drop operations. Press Manual Assembly Mode button. Then, the stiffness matrix and force vector are vacated for new assembly. Select an element, drag it, with the left mouse button pressed, and drop it into stiffness matrix window. Then, each of the squares representing the element entries moves toward its final position in the system equations. The assembly can be proceeded in an arbitrarily selected order of elements. The newly assembled entries are drawn in red color. The applied forces can also be dragged and dropped into the force vector in a similar manner. This drag and drop operation can be repeated, one by one, for all elements and applied forces. Click Manual Assembly Mode button again, to turn off the manual assembly mode. The numerical values of the matrix entries can be displayed, in place of the squares. Press Display Text button, then, all the squares are converted into numerical texts. The text format can be selected from the drop-down list. The actual entry values are equivalent to the displayed values, multiplied by the multiplication factor, which is predetermined for efficient display. All the operations demonstrated so far with the square display are valid also for the text mode. For example, if you place the cursor over an element in model image, the entries associated with the element are highlighted in blue color. In manual assembly mode, the element stiffness matrix can be assembled in text format by drag and drop operation. In text mode, the matrix entries are displayed in numerical text all the time. Thus, you may observe the actual values of matrix entries computed through the solution process. Press Decompose Stiffness Matrix button. Then, the matrix image shows the numerical values obtained by the Gauss elimination. Scroll the image to the left to see the force vector after the elimination. Press Back Substitute button. At this stage, the entries of the force vector have been replaced by displacement values, representing the nodal displacements. In order to get out of text mode, press Text Mode button. The matrix entries are represented by squares again. Let's examine alternative methods of matrix assembly. The drop-down list shows 6 alternative modes of display. Symmetric square matrix option is identical to square matrix option except that only the upper triangular entries are displayed. Band matrix option stores the matrix entries within the half bandwidth in two-dimensional array. This scheme reduces the computer memory requirement in comparison with original square matrix option. The memory requirement is shown in the window. Skyline option reduces the memory requirement further, as can be confirmed by the values displayed here. Skyline assembly and symmetric square assembly can be compared with each other, side by side, using symmetric plus skyline display option. The symmetric square assembly is displayed on the left, and the skyline assembly on the right. Click an element. Then, entries with contribution of the element are highlighted in red color, in both sides of the display. Click a node. Then, the entries associated with the node are also highlighted in red color. If you click an entry in the symmetric square assembly, the corresponding entry in the skyline assembly is highlighted in red color. And, vice versa. The diagonal entries in the skyline assembly can be mapped with the square assembly. Such examination helps understanding the rule of positioning the entries in skyline assembly. As an example, entries in skyline assembly can be traced by clicking the entries upward along a column in symmetric square assembly. Sequential allocation of a column can be identified in the skyline assembly. Frontor Solver option is used to simulate the process of assembling and solving equations by frontal method. The method uses not only the main memory, but also the secondary computer memory such as hard disk. In this graphics simulation, the left space represents the main memory, and the right space represents the secondary memory. The element matrices are assembled in the main memory. Differently from other assembly methods, frontal method proceeds with assembly and Gauss elimination at the same time. While element stiffness matrices are being assembled, Gauss elimination is executed for the degrees of freedom with complete assembly. The eliminated entries are vacated from the main memory and stored in the secondary memory for later back substitution. As shown in the window, the assembled entries are stored first in the main memory and moved to the secondary memory after Gauss elimination. Let's examine the animation of assembly and solution process, with control of animation speed. From the animation, we can observe that only a part of the assembled element stiffness matrices are kept in the main memory at a time. Because some parts of the assembled matrix are continuously eliminated and transferred to the secondary memory. Let's go through step-by-step assembly simulation for more close examination of the process. The stiffness matrix of element number 1 is assembled. Completely assembled nodes are marked by a small circle. Now, one node is completely assembled. Newly assembled entries are represented in red color. The completed entries are represented in blue color, and ready for Gauss elimination. The Gauss eliminated entries are moved to the secondary memory. This process is repeated for all rows and columns of the assembled entries. The next element is assembled, filling the unoccupied memory space, including the space vacated by the elimination. Previously assembled entries are represented in black, and newly assembled entries are overlaid in red color. An additional node is complete assembled. Thus, completely assembled entries are eliminated again. The third element is assembled. There appears an additional node, for which the assembly is completed. The procedure of assembly and elimination is repeated for each of the elements in the order of element number. The number of degrees of freedom actively stored in the main memory is called frontal length. The frontal length fluctuates in the course of assembly and elimination process. The maximum frontal length is an important factor determining the required memory space and computing time for solving equations. The maximum length depends much on the element numbering. Because the element stiffness matrices are assembled in the order of element number, the order of assembly can be manipulated arbitrarily in manual assembly mode. Press manual assembly mode button. Let's observe how the maximum frontal length changes if the elements are assembled in different order than the originally numbered order. Select an element and assemble the stiffness matrix of the element by drag-and-drop operation. The elimination has not occurred up to this step. No entries are eliminated, and no memory space is emptied for new assembly. Thus, additional memory space should be secured for assembly of another element. As the simulation goes on, the frontal length increases up until the elimination starts. The frontal length reaches its maximum, and reduces thereafter. Through this simulation, it is noted that the maximum frontal length depends on the order of elements for assembly. The element number optimization is the process of renumbering elements for minimization of the maximum frontal length. Let's compare the maximum frontal length between the original and optimized element numbering. Click Manual Assembly Mode button to terminate manual assembly mode. The stiffness matrix window shows the memory space of the Frontor Solver with the current element numbering. Choose Show Number Item from View menu. The element numbers are displayed. Let's execute element number optimization by selecting Optimize Element Number Item from Solve menu. Now, the optimized element numbers are displayed on the model image, and stiffness matrix window shows the reduced memory space. Let's switch back to the symmetric square assembly option. In the case of the square matrix or skyline assembly option, the required memory space and solution time are determined by the node numbering. So, let's check the node numbers. First, press Node Selection button, and choose Show Number Item from View menu. The node numbers are displayed over the model image. The half bandwidth is a factor, measuring the required memory space and computing time. Let's execute node number optimization by choosing Node Number Optimization Item from Solve menu. The optimized node numbers are displayed, and stiffness matrix window shows the reduced half bandwidth. This is the end of the screen demo about the educational function of Visual FEA to study the assembly and solution of system equations with a two-dimensional frame model.